In today's video, we're going to cover the 3 kinematic equations you need for solving any motion problem where the acceleration is constant. We'll start off where we left off last time with the calculus-based definitions between displacement, velocity, and acceleration. And if you missed that video, I put a link in the description below. Then we'll see how these calculus-based relationships simplify into 3 nice, tidy algebraic expressions. Some people like to skip these derivations and just run with the results. You can, by all means, do that, but it's kind of like running with scissors. You'll probably be okay, but I wouldn't trust you. Hi everyone, this is John, and welcome to my channel, drjohn.dev. I have a PhD in physics, and have been helping students solve problems in physics for over 15 years. Make sure to subscribe to my channel, and hit that like button. So the form of the kinematic equations most often used, especially in physics classes, is the special case of when a moving object's acceleration is constant. Having a constant acceleration turns out to have a wide application base in the real world, and even includes all objects in freefall near the surface of the Earth. So this isn't a drastic restriction on the applicability of these equations. However, this is a restriction. Some people take the constant acceleration assumption to mean all objects must accelerate at a constant rate in any scenario, and this just isn't the case. So before getting started, keep in mind the range of problems these equations can apply to, those with a constant acceleration. So why make acceleration constant in the first place? By making this assumption, the calculus relationships between displacement, velocity, and acceleration drastically simplify into nice, simple algebraic expressions. These systems of equations are known as the kinematic equations. Kinematics is a name of French origins and was first coined by the Frenchman André-Marie Ampère, who is most known for formulating Ampere's law in electromagnetism, as well as having the SI base unit of current named after him. While his greatest impact was in electromagnetism, a little-known fact is that in his work, Essay on the Philosophy of Science, he also helped coin the word kinematics, where he derived the root from the Greek word kinema, meaning movement. With that out of the way, let's derive the first kinematic equation relating velocity to acceleration. We can begin with the calculus relationship between acceleration and velocity, namely that acceleration is equal to the first derivative of velocity with respect to time. Now, we can integrate both sides over a time interval dt. For the limits of integration, we can set the initial time equal to 0 seconds and the final time equal to some arbitrary time t. Since the acceleration is constant, and this is exactly where that assumption comes in handy, we can pull the acceleration a out of the integral on the left-hand side, and the right-hand side reduces to an integral over dv with limits of integration from v at t equals 0 to v at t equals t. The integral on the left integrates to t minus 0, and the integral on the right integrates to v of t minus v at t equals 0. Now, instead of writing v at t equals 0, the most common convention in physics is to define this quantity as v naught. This is often referred to as the initial velocity, and if the object is starting at rest, this will be equal to 0. So after making this substitution and simplifying the algebra, this can be solved for v of t to find the first kinematic equation, which is v of t is equal to acceleration times t plus v naught. Notice, this is a linear equation, and if velocity were plotted versus time, v of t would simply be a straight line having a slope of a. We can derive the second kinematic equation in a similar manner as the first one, but this time we can begin with the calculus relationship between the velocity and the displacement, or v equals dx dt. We can integrate both sides as we did before, but this time we can't simply pull the velocity term out of the integral. If you look at our first kinematic equation for v of t, we see that v is a function of time. So we can use this equation to substitute in for v in the integral. and then we'll be able to integrate. Upon substitution, the integral on the left-hand side has two terms, and the integral on the right-hand side reduces to an integral over dx. We can break this down and evaluate each term one by one. Let's begin with the first term, a0 t. The acceleration again factors out of the integral, and t dt integrates to t squared over 2. And after substituting the limits of integration, this evaluates to 1/2 a0 times t squared. Let's just hold on to that result for now. The second term is the integral of v0 dt. Since v0 is a constant, this can be factored out of the integral, and after evaluating from t equals 0 to t, this becomes v0 times t. We can save this result as well. Finally, the right-hand side is simply over dx. The only thing to note here is that we can define the limit of integration, x at t equals 0, as simply x0, similar to how we defined v0. This can be thought of as an object's initial starting position. So after making the substitution, this integral simply evaluates to x of t minus x0. So bringing everything together now, we can solve this expression for x of t. This brings us to our second kinematic equation, which is x of t is equal to 1/2 a0 t squared plus v0 t plus x0. Now, we have an expression for v as a function of time, and we have an expression for x as a function of time. And we know acceleration is constant in time. So you may be wondering, what else is left? Well, there's one more kinematic equation that can come in handy when you're not explicitly given a time t. That is, you can form an equation of velocity as a function of position, or v of x. To do this, let's consider a derivative of velocity with respect to x, or dv dx. We can multiply this by a factor of dt over dt, and then rearrange the differentials as dv dt multiplied by dt dx. Notice, the first factor, dv dt, is simply the acceleration, which is a constant a0. The second factor, dt dx, is the inverse velocity, or 1 over v. Setting these new factors equal to the original expression gives us a separable differential equation. To solve this, we can multiply both sides by v, and then integrate both sides over dx. Starting with the left-hand side of the equation, the integrand becomes v dv integrated from v0 to v. This evaluates to v squared over 2. And after substituting the limits of integration, this becomes 1/2 times the quantity v squared minus v0 squared. The right-hand side of the equation is simply the constant a0 integrated over dx. So this then becomes a0 times x minus x0. Bringing both sides together, we can algebraically solve for v squared, which will be our final kinematic equation relating v as a function of x. This expression is typically left in this form, with the square root not performed on both sides. So we can stop here and box this equation. And there we have it, the three kinematic equations of motion for when acceleration is constant. And under this condition, you can solve any kinematics problem, so it's worth memorizing them. Each equation is useful depending on the known and unknown variables for a particular problem. For instance, you can use the first equation to find an object's velocity v after a certain time t, and you're not given the displacement the object traveled during that time. The second equation is useful for when you want to find the object's displacement at a certain time t, but aren't provided with the object's current velocity information. Finally, the third equation is often the most overlooked, but equally as useful as the first two. It's best to use when you want to find the object's current velocity, but are only provided with the object's displacement rather than the time of travel. Working through a few examples can really help highlight how these equations can work in action. Next time, we'll go over a couple of these examples and also cover when you can and can't use these kinematic equations with constant acceleration. So if you want to catch that video, make sure to subscribe to my channel. Thanks again for watching, and until next time, happy learning.